All right, so today we're going to actually write and do things by hand, and this is why it took me a little longer to connect all of my tablets in order to be able to, whatever I write, project on the screen and capture by video. So let's see how that works. So, and you will also see me trip over all of these wires here that are set up. So, what we're going to learn today is a procedure called Gaussian elimination. And that is basically a solution procedure that will transform initial, so we are tasked, so for solving AX is equal to B. And when I say AX is equal to B, what is A, what is X, what is B? A is a matrix, X is a vector of unknowns, and B is another vector. And what AX is equal to B is basically a short way to write down a system of linear equations. So we have introduced them last time. So basically the system of linear equations, so this stands for something like A11 x1 plus A12 x2 plus all the way A1 n xn is equal to B1. That is my first equation. I also simply get it by multiplying the first row. When I'm multiplying matrix A and vector X, I get it by doing a dot product of the first row of matrix A and the column vector X, right? And then I have the second equation. And this B1, B2, that's my right-hand side. That's the elements of vector B. The best here is that I will press things and I will have no clue what I pressed. And it happens to me all the time. X, there we go. Let me redo a couple of things. Undo. Yeah, I'm just gonna rewrite again. Gaussian elimination for AX is equal to B. So by AX is equal to B, I mean a system of equations, A11 x1 plus A12 x2 plus all the way to A1 n xn is B1. I will not write the second one, I will just write this last one. So I have n equations, n unknowns, and I know the coefficients A11, A12, A1n. I'm tabulating them into a matrix, okay? Because by now we know that matrices are efficient structures that we can define a lot of things with. And then I have this vector B on the right-hand side. Those are also known coefficients. So A and B are known coefficients, and what I don't know is x1, x2, xn, and I want to find x1, x2, and xn that is simultaneously solving n equations at the same time. And we've seen last time in our playing with smaller systems that if I'm thinking about 2 by 2 systems, so when n is equal to 2, then what I'm really looking for is intersection of two lines, because each of these equations is defining a line, and if those lines are not parallel, or if those lines are not the same, okay, I can find an intersection, a single point that is at the intersection of them. If I have a 3 by 3 system, I'm now searching in three-dimensional space, and I have to intersect planes. And again, if they're not parallel, and if they're not all, so basically if equations cannot be obtained, if I can obtain one equation by a linear combination of the others, multiplying through them by two different coefficients and adding them up, then they're linearly dependent, so they're not giving me any new information. If they're linearly independent, I will be able to find this unique point at the intersection of three planes in 3D. And I can keep going. In math, I can always keep going. Whether I can store the results or actually search for it efficiently in the computational world, that's another question. But in our thoughts in math, we can always keep going to infinity. And basically, we'll just deal with hyperplanes in n-dimensional space that we're going to intersect. Okay, so back to the real world, we're just simply looking for solutions of these. A lot of engineering problems and scientific problems can be expressed as sets of linear equations. Of course, sometimes they're sets of nonlinear equations, in which case we're often busy linearizing them and then still using these methods of solving linear systems, simply because of the complexity and time it takes to actually look for those. So we will now first actually devise a procedure of how to solve things by hand, and then we can figure out how to write it in a structured way as an algorithm, so that our computer, or rather our Anaconda Python notebook, okay, will be able to tackle any system of linear equations that comes our way, and basically just do things for us as opposed to doing things by hand. Because we really do things by hand up to 3 by 3 or 4 by 4. Other than that, our time is better spent programming how to do this efficiently without doing things by hand. So let's get going. So this is, again, Gaussian elimination is a solution procedure. And it basically transforms the original system of linear equations to essentially either upper triangular system. If you remember, upper triangular system is the one where the corresponding matrix A has basically a whole lot of zeros in the bottom below the diagonal, or rather all zeros below the diagonal, or even diagonal system. We're not going to go to the diagonal, but we could probably proceed with our procedure. And those are basically less involved to solve to an upper triangular system. Well, and again, I'm pressing, and I don't know how to spell triangular.
What is that word?
Upper.
No, that transformed to what?
The original system.
The original.
The original system.
To an upper triangular system that we can solve using back substitution. And I'm throwing a whole lot of new terms at you. Back substitution, upper triangular system, Gaussian elimination. They're probably new if you don't remember that I mentioned them last time. So it's going to take a moment for you to remember them, but you've seen them already, and we actually used them on that worksheet on Monday already. So let's simply start with an example. That's the best. So I'm going to use a three-dimensional example, and my system is as follows. Minus 3x1 plus 2x2 minus x3 is equal to minus 1. 6x1 minus 6x2 plus 7x3 is equal to minus 7. And 3x1 minus 4x2 plus 4x3 is equal to minus 6. I'm going to wait a moment for everybody to write down. So basic idea is the following, or this is our guiding thing. Every time I'm multiplying one of the equations with a constant, I'm not doing anything to the solution of the system. Okay? I can do that. I can multiply, I can divide as long as I'm not using 0. Okay? I can also multiply one of these equations and with one constant, another one with a different one, add them up. By that way, I'm actually creating a linearly dependent equation that is not adding anything new, but I can replace one of the equations with that one. Okay? So I'm going to use this freedom to actually create a system that has a little more zeros than this one, because when zeros are there, it's easier to solve. It really comes down to that. Okay. So first thing, and it's very similar to solving those 2x2 systems when you were eyeballing things to subtract or add or to eliminate one of the unknowns. So basically that's what we're going to do. And we can just eyeball. We can also create a system. So for programming this, we're going to have to be consistent. And computer doesn't care whether the number is nice or not nice. Computer will do it anyway, right? so we don't have to take care of our computer emotional well-being by looking at numbers that are ugly or not ugly, right? But if we're doing it ourselves, we can kind of pick and choose numbers so that it's like nicer to work with. So first things first, I don't want to drag along these numbers x1, x2, x3, and if I'm actually using matrices and keep things in their columns, that can keep things in order without me writing down x1, x2, x3. So I'm going to actually write down a so-called augmented matrix that has all of these coefficients in without writing down x1, x2, x3. So this is my matrix A, and I'm going to also have sort of like a separating line, just really visually. And then I'm going to put B on the other end. Okay? So this is my A, and this is my B, and this is called augmented matrix. This doesn't mean that I didn't write x1, x2, x3, but because I'm using a matrix, I know very well which column corresponds to which unknown. It goes without saying. Okay, so that just shortens writing. Now, what can I do with this? Let's say that my objective here is to create an upper triangular matrix. So essentially, I want to these three numbers, I want to somehow transform into zeros. Okay? Great. So one thing that I can do in terms of linear combinations, I could multiply the first row by 2, then I'm going to get minus 6. and add it to the second row, and that will zero out coefficient in this first column. So let's just do that. And what I'm doing is I'm replacing one of the rows with a linear combination of that row and another row. I'm allowed to do that. I'm not going to change the solution to my system if I do that.
Upper row echelon.
Yes, so I can do that. Those were called upper row echelon forms in your linear algebra class if you had one. So we will replace this row with, now, okay, let me get in tune with your linear algebra class. If you had a linear algebra or differential equations, did you call these rows R1, R2, R3, yes, something like that? Okay, let me switch to that. So I've been using Roman numerals 1, 2, and 3 because that's what I used. I'm not going to say how many years ago in my linear algebra classes that stuck with me forever. So I'm going to try to change here. So you're saying I should use R1, R2, R3. Let me do my best to do that. So I'm going to say replace this row R2 with 2 times row 1 and plus row 2. Okay. And what I can do with the row below is just add them up. So we're going to replace with just simply row 1 plus row 2. And I'm going to write it down explicitly. This does not alter solution to the system.
Don't you mean R1 plus R3?
Correct, that's what I meant, but that's not what I wrote down. I was just testing you, yes. I'm gonna stick to that story. Okay. Sounds better than the one I just mistyped. Okay. All right. Finding a good story is an important thing. All right.
Now, when you say this does not alter the solution to the system, what do you?
So if I have x1, x2, x3 that are solving any of these equations, or rather all of them at the same time. So in particular, if I have x1, x2, x3 such that first row is true, minus 3x1 plus 2x2 minus x3 is equal to minus 1. If I multiply that entire thing by a number and add it to another row that is also true, I'm still getting an equation that is true for that same x1, x2, x3. So I have not, for the solution that solves R1 and R3, it's also solving R1 plus R3. That's what I mean by linear dependence of these rows. But this R1 plus R3 is not bringing me new information, so I can just replace one of these rows. In this case, I'm replacing row 3 with R1 plus R3. Does that make sense? So I'm just altering things a little bit to make it easier for me to solve, but I'm not changing the actual solution in itself. All right, so let's actually do that. Stop talking, just do what you promised to do. So now if I have minus 2 times, or 2 times minus 3 is minus 6 plus 6 is a 0. 2 times 2 is 4, minus 6 is minus 2. 2 times minus 1 is minus 2, plus 7 is 5. And then on the right-hand side, this is my b. I have to change b at the same time. Our coefficients is b. It's negative 9. Thank you. Now let's do that. It's a simpler business for the third row. I'm replacing it with R1 plus R3. So minus 3 plus 3 is a 0. That was by design. 2 minus 4 is minus 2. Minus 1 plus 4 is 3. Minus 1 minus 6 is minus 7. I will proceed. And I will now try to eliminate -2 in this location here by the same thing. So I can simply multiply the first row by -2 and add it to the third row. These are my new transformed rows. I can also do the other way around. Second row minus third row. Both work. Okay? So I'm gonna stick with my original choice and say replace here with row 2 minus row 2 plus row 3. And I'm gonna squeeze in things here so I don't have to rewrite. So I'm gonna keep the others the same. So 2 minus 2 is 0, that's by design. -5 plus 3, that is -2. And 9 minus 7 is 2. This is what I call upper triangular form because everything below a diagonal, these are diagonal elements. In my matrix A, everything below is 0. Quite frankly, lower triangular form would work fine too. But we will stick with this procedure. So what I can do now is what we did last time when we solved things on that paper. Basically, I'm going to start with the row that is easiest to solve, which happens to be the last one. So I'm just going to find x3 from that row. Once I know x3, I'm going to plug it into the one above and keep going. You might have had another class where you basically also use the similar procedure to just eliminate and make zeros above. That really works too. But we're going to use this for reasons that will become a little more obvious later. So I'm going to just save this now and open a new paper. So now this is upper triangular form. We start back substitution. So basically last equation was -2 if you remember. So this is -2x3 is equal to 2. That's what it's equivalent to. So that gives me x3 as -1. So that was my R3. Now my R2, so that plays into R2. R2 tells me that -2x2 plus 5 times x3, which is -1, is equal to -9. Please look at your notes and verify that that's indeed the case. And I'm not selling you here snake oil. So we had coefficients -2, 5, and -9 in that second row. And there was a 0. It's really 0 times x1, by the way. Right? So whatever x1 might be, doesn't matter. So that basically gives me that -2x2 is equal to -4. And x2 is equal to 2. And that both of those solutions will play into my first equation, or my first row. What does it say? Who can help me out?
-3x1 2x2.
Okay. No. Just a moment. It's at 5.4%. Enter, no.
Image size, maybe.
Okay, let's try. Uh-huh. That's pencil. Oh, this is close. Come on. Okay. Getting there. It is hilarious how it's sensitive to that one move that I brushed something, but I cannot do it very quickly when I do this. All right. So we had minus 3x1.
Plus 2x2.
So my x2 is 2, so that's 2 times x2 is 4. And minus 1 times minus 1, so that's plus 1, is equal to negative 1. So that is minus 3x1 is equal to minus 6. So x1 is also 2. That is our solution. How do I verify that that's indeed a solution?
Plug them into the original equations.
Right. So who can plug them into my second equation? What was the second equation, the first one that I write into?
6x1 minus 6x2.
Plus 7x3. What is that equal to? So my original R2 so 6 times 2 minus 6 times 2 plus 7 times minus 1 is minus 7. That indeed is the case. So here I'm doing a lazy version. I'm checking only one. I'm going to call it a day. But that doesn't mean that I checked them all, just for the record. Okay, so this is the basic procedure. That's it. Except that it's not. We can run into a couple of problems. So let's now see what happens if I have something like this. So I'm going to have a problem saying 2x2 plus 3x3 is equal to 6. And now what did I do? I don't even know. Okay. Is 6. And then 4x1 plus 6x2 plus 7x3 is equal to minus 6. 2x1 minus 3x2 plus 6x3 is equal to 2. So I can put this to my augmented form so I don't carry around or keep writing things that I don't feel like writing. So now I want to make this an upper triangular form. What do I do? So I want to make a 0 here, 0 here, 0. How can I do that using my first row? What can I multiply a 0 with and add to whatever other number to make that other number 0?
Can't.
But what can I do? Does the order of these equations matter?
No, you
So
can
we'll do that. So this is called partial pivoting.
So real quick, for that last one, we find those to be the answers. How would you want us to write that? How would you want us to write the answer to that?
Answer to what?
Just like that. Just
Box
how you have
up. Yeah, x1, x2, x3. If I ask you, so just the solution of the system, if I ask you a vector form is 2, 2, minus 1.
Okay.
So that's vector. Alright, so back to the problem at hand. Nothing happens if I reverse the order of rows. Okay, so I can freely do that. Just exchange. And that's, I'm going to say this is similar to system 4, 6, 7, minus 6, 0, 2, 3, 6. And the third remains what it was. Well, the good news now is that I already have a 0 in one of the places that I wanted, so it's a shorter work to get it where I need it to be. So I'm going to work on this. What can I replace this row with so that I can 0 out this 2 by using first row? I could divide. I don't want to divide number 7.
Oh, yeah.
So this is the choice part, right? If a computer was doing it, who cares? But if I'm doing it, I'm just going to say maybe multiply this third row by 2, right? So we're going to say negative row 1 plus 2 times row 3. How's that?
Yep.
Or the other one, I could do row 1 minus 2 times row 3. I have infinite number of possibilities, but I'm picking the one that kind of appeals to me right now because I'm doing things by hand. Once I'm a computer, I can't do that anymore, okay? But I'm a human. And humans make mistakes. If the numbers are nicer, they're going to make less mistakes. That's something to take into account. That's the reality we have to work with, okay? So, negative 1 times 4 is minus 4, plus 2 times 2 is 0. That's by design. And then I have negative 6 plus 2 times minus 3. That's negative 6 minus 6. That's minus 12. Negative 7 plus 2 times 6 is 5, I believe. And then 6 plus 2 times 2, that's 10. Yes? All right. I have one more to work with. So now I'm actually working
R3 plus 2.
to make this a 0. So, and I'm working with the second row. Why am I working with the second row? Because I have a 0 here that is not going to mess up this 0. Formally, I could work with first one, but then I would go in circles and I would never arrive at that lower triangular. I would not be changing the solution of the system, but I would not be getting closer to finding that solution either, okay? So no big damage done except a waste of time.
So it'd be R3 plus 6 R2s.
You're saying R3 plus 6R2. I can work with that. So I'm just going to specify 6R2 first because just going in order. Plus R3. So I'm going to rewrite my first two. So 6 times 2 minus 12 is 0. 6 times 3 is 18. Plus 5 is 23. 6 times 6, 36. Plus 10, 46. All is well, 46 is divisible by 23, so I'm not going to have to do. Okay. Everybody got this? So now I attack things with so-called back substitution. So my 23, my row 3, says that my 23x3 is equal to 46. X3 is still 2. So then I use that in my row 2. And I have my 2x2 plus 3 times 2 is equal to 6, correct? So my x2 is, these two things cancel, my x2 is 0. And R3 says 4x1 plus 6 times 0 plus 7 times 2 is equal to minus 6. So my 4x1 is minus 6 minus 14 minus 20. X1 is equal to minus 5. And if I wanted to write this down as a vector solution, then my x is minus 5, 0, 2. So I got the same thing as my notes say I should get. I'm going to use that as a verification. Otherwise, you plug in. Now, if you were solving a homework, make sure to plug in. You can also simply put this into Python, the matrix A, then this vector x that you got, and the vector b that you got, and verify that A times x is equal to b. Okay? You can verify it by hand. You can verify it in some way, but verify it. If you're on the exam, whether you verify or not depends on the time you have. So you do your time management on the exam. Because if your verification says, oh, you messed something up, that means that you made a small mistake on the way, and then you need to go back and fix it. And maybe your time is better spent trying to solve a different problem. Okay? That's your time management on the exam. As we know, exams require both knowing the procedure and being accurate. Okay. Now, last thing that I would like you all to think about is that, okay, great. So we have to now start thinking about how I'm going to attack solving this. Okay? So both the procedure in getting to upper triangular matrix, or this row echelon form, it requires figuring out what coefficient, so I'm working with one element at a time that I want to zero out. Okay? So I have to figure out, hey, which column I'm in, right? Which element, which column. And then I want to figure out, hey, what is the coefficient to work with? Right? Now, when we are eyeballing things, we're just eyeballing things. And we kind of follow, we can solve this probably just following intuition. We're still going to allow. But the intuition is not a good algorithm, okay? Not for computer. With computers, we know that we have to give them strict procedures to follow. And also, we have to kind of think about, okay, well, what if you encounter a zero that you cannot work with? Then you have to instruct the computer to flip two rows. Okay? So I have to exchange elements. Okay? So let me just, as a guiding sort of light, try to work with something more generic. So how to program this, right? So let's say that I have just a 3 by 3, but for a computer I actually want to have something bigger. So I have A11, A12, A13, and B1, A21, A22, A23, B2, A31, A32, A33, and B3. So now let's say that I want to zero out this element. Now if there were numbers here, 2 and 3, I would figure out that I'll multiply 2 by minus 3 and add, or something of that sort, right? Well, computer doesn't function that way. Okay. What do I tell computer? So let's say that I want to find coefficient. So I want to replace this by some coefficient C times row 1 plus row 2, with the objective of making A21 0. How do I set up that equation? How do I find C? So C times A11 plus A21 will replace my A21. Is that correct? Which I want to be 0. Can you find C now? Yes. So ask your question, write it down if needs be, and then translate to what it comes down to, right? So my C is minus A21 over A11. And maybe these numbers don't divide nicely. Who cares? Computer doesn't care. Okay? So if I multiply my first row by minus 2A21 divided by A11, obviously when I multiply by A11, this part will go away. And plus A21 will give me a 0. Yes? So for my second row, that's the C I need to have. What about the third one? I want to so maybe I should call this C2 if you will. So what is my C3 times R1 plus R3? What is my C3? Give me half a minute or answer it quickly. Again, this C3 times A11 plus A31 has to be 0, right? That's what I'm designing. That's what I want. So what is C3 then? Do we see a pattern? If I had more rows, I would just keep going. So we'll need to program that with a nice little for loop. Okay? And once we do, then we can solve a 100 by 100 system. Okay? All right.